Okay, so let's do this problem here. So what we have is a vertically oriented pressure vessel. It has, so it's 6 meters tall, 1 meter in diameter with a 20 millimeter thickness, so inner diameter of 960 millimeters. And it has a couple of loads applied to it, obviously. So first off, it's got a wind load. So, it's sitting there and it's wind's blowing on it. So that's going to be applying a distributed force of 500 newtons per meter, per meter vertically. 500 newtons per meter of height. It's also got this bracket that's welded onto it at 4 meter height, and that one is, it's on the positive X side. And then we have a force, like a cable or something attached to that bracket that's applying a force to it, and that force is 10 kilonewtons oriented in the negative Z direction. As well. So the tank has a mass of 300 kilograms, 3,000 kilograms, and it is pressurized up to 1.5 megapascals. So overall, we want to basically examine the stress state at the base of the pressure vessel and figure out where the highest shear stress is and what the stress state is at that point, the location with the highest normal stress, and what the stress state is at that point. So the first thing that's fairly easy to do is to figure out what sort of axial force we're going to see due to the weight of the object. So that obviously that is going to be acting in the y direction. So it's going to be a compressive force in the y direction. Magnitude of that is just based upon the mass, so 3,000 kilograms times g, 9.81 meters per second squared. Obviously, kilograms times meters per second squared gives us newtons, and all that divided by the cross-sectional area. So the cross-sectional area, obviously, it's the area of a 1 meter circle minus the area of a circle with 960 millimeter diameter. So in diameters here, obviously divide by 4 there because we're working in diameters and not radius. So that ends up being 29.4 kips divided by 61.5 thousand millimeters squared. That works out to 0.048 megapascals. So that's a negative 0.48 megapascals because it is compressive. Next up, axial force due to pressure. So we've got the longitudinal, which is also acting in the y direction. So that's just P times R divided by 2T. We're assuming it's a thin-walled pressure vessel, and considering that the ratio of the radius, the ratios of the radius to the thickness is sufficiently high that we can do that. So 1.5 megapascals times 500 millimeters divided by 2 times 20 millimeters. Millimeters cancels out. This gives us 18.75 megapascals. So that's the longitudinal stress. We got the hoop stress as well. So hoop stress is just double the longitudinal stress because you don't include that 2 there. So that'll be 37.5 megapascals. And then we want to figure out what sort of equivalent loads are being applied if we had them at the base instead. So for the 10 kilonewton force, obviously the shear force there would be 10 kilonewtons, also in the negative Z direction. And that thing is also going to be applying a moment. So again, if we apply this force here times this moment arm here. It is going to be causing rotation about the x-axis in this direction. So, which is the opposite of what our which is the opposite of what we'd see with our right hand rule. Right hand rule would be positive that way. So that is a negative moment being applied. Negative bending moment. Magnitude is 4 meters times the 10 kilonewtons, so negative 40 kilonewton meters. That's our bending moment. And next up we have the torsional portion of that stress, of that force. So basically, if we are applying a moment this way, it is going to be causing a moment about the y-axis. So again, the y-axis is oriented this way out of the page based upon our little coordinate system here. So that is a counterclockwise force, and that results in a positive moment about that axis. So magnitude is 6.6 meters times the 10 kilonewtons, or 6 kilonewton meters. So we've also got the wind load to worry about. So again, its magnitude is going to be based upon the 500 newtons per meter distributed load times the 6 meters over which it's acting. So it's a 3 kilonewton force. So the shear caused by that is 3 kilonewtons. It's also going to cause a bending moment. So that bending moment's magnitude is going to be 3 kilonewtons times the 3 meters. Again, half of that distance. So it'll be 9 kilonewton meters. And again, our directionality here, it is pushing this way about this point. So that's a clockwise. So about the z-axis, that is going to be a negative moment. So negative 9 kilonewton meters about the z-axis. So any of our rotation about the x-axis or the z-axis is a bending, and any rotation about the y-axis is torsional, just because of the orientation of the thing. So we basically just need to figure out what sort of effect our direct shear is going to have. So we're talking the direct shear here. So it is pushing 3 kilonewtons this way and 10 kilonewtons this way, which means that the resultant here is 10.4 kilonewtons. And the orientation of that resultant, that's 73.3 degrees from the positive x-axis. So for a thin-walled pipe, your variation in the shear, it varies. The way the shear flow works is that it varies from 0 to 0, and then kind of maxes out and then drops down like this. So you're going to have your maximum, at a point that is perpendicular from the directionality of the thing. And the magnitude of that maximum ends up being 2 times the average shear. So 2 times the shear load divided by the area. So you could look that up if you want, or you could derive it just by calculating your shear flow. Either way works. Obviously, looking it up is usually going to be a bit quicker. So the magnitude of that, again, 2 times the 10.4 kilonewtons, so divided by our area, which we calculated up here. That gives us 0.34 megapascal. So again, and since we're looking at this, y-axis is about here, so counterclockwise is positive. So basically, when we kind of define it, so it's going to be positive over here and negative over here. So the variation of the shear based upon the position just needs to be 0 here and here, and it needs to be maximum, the tau max here, and it needs to be negative tau max here. So how we do that, I got it's a trigonometric relationship. So we got 0.34 as our amplitude, and then just cosine of theta times theta plus 16.7 degrees for here. So that basically, here at negative 16.7, this ends up being 0, so this ends up being 1. On the other hand, over here at whatever 180 minus, what is that? Over here at 163.3 degrees, that ends up being 180. So this ends up the cosine term ends up being -1, which means that we've met our relationship. And conversely, for here and here, both of those end up being 0. So yeah, and just measuring theta from the x-axis. And then we've got our torsional. So torsional stress is equal to the torque times the C divided by J. So relatively straightforward. The C that we're going to use is the outermost area. So the outermost radius of the tank, so the 500 millimeters, and then J just calculated based upon the radii as well. So that ends up being 0.41 megapascals, and again that's basically acting. That's going to be constant at any point along the outside of that skin, pushing it in a counterclockwise direction, so positive. Next up, we got the bending stress. So we got the two bending moments. We got so again, with our x in this direction, our z in this direction, we have a -9 kilonewton meters in the z, and we got a negative 40 kilonewton meters in the x. So basically the overall bending moment that we're applying is about this axis. So that means that we have so the magnitude of that resultant there is 41 kilonewton meters, 9 square root of 9 squared plus 40 squared, and basically the angle between the x-axis and the neutral axis there is 12.7. So it's just inverse tan of 9 over 40, or -9 over -40. Gives us that angle. So again, that'll induce bending stress in the y direction. The maximum compressive will be there. The maximum tensile will be there. So at any point, so if the neutral axis is kind of located there, then the position from the neutral axis to any point based upon the angle, so the maximum amount is 500. That'll be just based upon the sine of whatever angle you're at here plus the 12.7 degrees. So it becomes maximum there, becomes minimum there. Negative displacement down there. So again, our bending stress just negative. Our negative times our negative 1 times our moment times the y divided by I. So here's just the term we had for the whatchamacallit, the y. Here's our moment in terms of oh, sorry, I realized that should say newtons right there. I threw in an extra 1,000 there so I could say newtons instead of kilonewtons, but I accidentally drew the kilonewtons. So yeah, everything here is in terms of newtons and millimeters, so that I can get a nice megapascal answer when we're done here. And then obviously our I is just based upon the radiuses that we're working with. Pi over 4 times the radius to the fourth of the outer minus the radius to the fourth of the inner. So that ends up being negative 2.77 sine times theta plus 12.7 degrees, which ends up again being negative negative 2.77 right here and 2.77 right here. So we've identified our points. We just need to calculate what the stresses are there. So at the point where we're having maximum shear, so again, the torsional shear, that's constant throughout. Whereas the direct shear, again, it's maximum magnitude here and here, but again, keeping the convention that the counterclockwise shear is positive. It's positive here, it's negative here, so this is the point where we'll have the minimum shear, and this is the point where we'll have the maximum shear. So the maximum magnitude occurs at a theta of negative 16.7 degrees. So, and the magnitude of that shear, that's going to be the 0.41 from the torsion plus the 0.34 from the direct shear, which ends up being 0.75 MPa. So at that point, we've also got hoop stress. So hoop stress is 37.5 megapascals, and then we're going to have the stress in the y direction. So the y direction, that's going to be a combination of the bending stress, the longitudinal stress, and the stress from the weight. So again, we'll be plugging in negative 16.7 for our formula here that tells us what the bending stress is. So negative 2.77 MPa times sine of negative 16.7 plus 12.7 degrees. So that ends up being a slightly negative value here, which means that our sine is slightly negative, which means that this overall term is slightly positive. But it's not much. And then the 18.75 and the negative 0.48 megapascals, giving us a final stress value in the y direction of 18.46 megapascals. So I've drawn a little element here. Got the y, 18.46. we got the hoop stress, 37.5, and then we got our shear. So shear obviously needs to be acting that way, and based upon the fact that that's the way we know shear works, we also need to have the shear acting in this direction. And then obviously on the opposite faces, we got opposite stresses. And again, we're working with a thin-walled assumption, so there's not going to be any force on this face, nor will there be any force on the face on the opposite side. So our stress state, in terms of the stress in the the radius direction, the theta direction, and the y direction. So radius, theta, y. It's all zeros for anything involving the radius. And then for our theta direction, that's the hoop stress. For our y direction, that's that stress. And then for the shear, the tau theta y and the tau y theta, that's equal to 0.75 megapascals. So that's at that point. Next, we got the point where there's the maximum normal stress. So again, that'll be where the bending stress is at its maximum tensile, since the combination of the weight and the pressure together result in tensile. The pressure is tensile, the weight is compressive, but the pressure's a hell of a lot higher than the weight. Well, the stress due to the pressure is a lot higher than the stress due to the weight. So in order to see our maximum values, we're looking at the point where the stress is the maximum positive value as well. So that'll be at theta equals 257.3. So right here. Right there. So the shear stress at that point, it's just going to be a direct plus the torque. So the direct based upon the maximum times the little cosine thingy to figure out how it varies from the maximum. Our torque is constant throughout, so that's the 0.41. So this is relatively small since that term ends up being pretty close to canceling out. So it ends up being 0.43 megapascals. Then we got stress in the y direction. So again, combination of the bending, the longitudinal, and the weight. In this case, the bending is positive at maximum, so just the 277 plus the 18.75 minus the 0.48, which gives us a y direction stress of 21.04 megapascals. And obviously the hoop stress stays the same. So just drawing this element here, again, kind of orientating it based upon the fact that it is, come on, where's my, let me change colors. Based upon the fact it's, it's located right here. So again, y direction 21.04, theta direction 37.5, and then our shear stresses are going to be 0.43. So theta, our sigma r theta y, our r's are all 0, our theta, our yy, and our theta y and y theta. And that is about that.